Welcome everybody. This is our sixth session in NEET previous year questions, fourth chapter, moving charges and magnetism of class 12th. Before this video, we have made 5 videos in this series and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for JEE previous year questions. So if some of friends you are preparing for JEE, then you can guide them through those videos. And you can also try those questions yourself. And if you like these videos useful, then do press the like button, share them, and subscribe to our channel. It helps a lot when you share and subscribe. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. And in the previous one, we completed up to around 50. So that was the one of the question which we solved. And today we will start with the question number 50. So here, this is the similar one as the previous one because the diagram is same. A square loop carrying a steady current I placed in a horizontal plane near the long straight conductor carrying a steady current I1 at a distance d from the conductor as shown in the figure. The loop will experience. So as in the previous one, you can watch our last question in our previous video. We found out that the net force is towards the wire or net. As a whole, the loop experiences a attractive force. So here the loop will as a whole will experience the attractive force because if I mark some points here A, B, C and D, then the wire AB will experience attractive force, the wire CD will experience repulsive force. But force of AB is greater as compared to CD, so as a whole, net attractive force will be there. And AD and BC will experience some force, but those forces will be equal and opposite. So these forces are torque forces. They will produce torque, but if we calculate the if we discuss regarding the amount of force, so their force will be equal and opposite, so as a whole that will be zero. So answer for this question is the net attractive force towards the conductor. Option D will be the right answer here. Moving to the next one. A long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per centimeter is halved, the new value of the magnetic field. So we know magnetic field due to a solenoid is given by this formula B is equal to mu naught N I. Here it is mentioned that current is doubled. So suppose new magnetic field is B dash. So current is doubled, mu naught stays the constant, and the number of turns per centimeter. Here it is cleverly mentioned as per centimeter. Now we know, suppose N is 100. It means 100 turns per meter, or we can say 1 turn per centimeter. Now, if we reduce this 1 turn per centimeter to half turn per centimeter as per question, then we will get 50 turns as we have a half turn in a centimeter, then in 100 centimeter, we will get 50 turns per meter. So if we reduce turns per centimeter to half, then turns per meter are also reduced to half. So N becomes N by 2 and magnetic field value will be mu naught and I. That is again same as the previous one. So option B will be the right answer here. Let's move to the next one. A uniform conducting wire of length 12A and resistance R is wound up as a current carrying coil of shape of equilateral triangle A and square of side A. The magnetic dipole moment of the coil and square we have to find out. So here we will discuss two cases. First for the, you can say, first we have a coil, a triangle, and then we have a square. So let's start with triangle. Now, as mentioned, it is an equilateral triangle. So perimeter of this triangle will be, suppose if length is L, so perimeter will be 3L. And as this triangle is made of wire, so total perimeter should be equal to total length of the wire. So we can say 3 of L is equal to 12A, and from that L is equal to 4A. Now we have to find magnetic dipole and magnetic dipole moment. So that is given by number of turns into current into area. Here we have one turn only. We will assume that current is I. Now we have to find the area. So area can be find out using, if we divide this triangle into two halves, then this will be 90 degree, and as this is equilateral, so this angle will be 30 degree, as total angle is 60 degree. So here we can say base will be L cos 30, or area of this triangle will be area of the one half of the triangle, that will be half. Base is L cos 30, that is L root 3 by 2 into perpendicular, that will be L by 2. So L by 2. So area will be root 3L square by 8. That is the area of one half. We have similar half also. So we will multiply it by 2. So root 3L square by 4. So N is 1. Current is I. And we have root 3L square by 4. So magnetic dipole moment will be, so it comes out to be root 3L square by 4. Now, okay, we forgot to take this into consideration. That equilateral triangle side is A, and I took it as L. So here side is A. It means, okay. So we have to do it again. So where is the rubber? Let's do it again so that there is no confusion. So now mentioned that size is A. So side is A. If side is A, their perimeter of the triangle is 3A. And we have been given that total length of the wire is 12A. So to cover the 12A length, we need such a 4 rotation. Only then we will be able to cover the length, or we can say number of turns will be total length of the wire and the perimeter of the wire, that is 4. So number of turns will be 4. Now we have N4 here into I. Now let's discuss regarding the area. Area will be half, that is for one half. Base is A cos 30, that is A root 3 by 2 into perpendicular, that will be A by 2. So it will be root 3 A square by 8, and we have two sides, two halves of the triangle, so it will be root 3 A square by 4. Root 3 A square by 4. So now magnetic dipole moment is root 3 I A square, that is for the triangle. Now for the square, side of square is also A, so square, as its side is also A, it means its parameter will be 4A, and we have been given total length of wire, that is 12A. So number of turns will be 12A by 4A, that is 3. So here magnetic dipole moment will be number of turns, that is 3, current I, and area is a square, so 3 I a square. Now if we match the answer, this and this, we have option A as the right answer. Now let's move to the next one. Wire of length L carrying current I ampere is bent to form a circle, the magnetic moment. So L is the original length of the wire and we bent it to form a circle. Suppose this is the circle and this circle has a radius equal to R. So circumference of this circle should be equal to the length of the wire. So 2 pi R is equal to L, or L is equal to R is equal to L by 2 pi. Now magnetic moment will be NIA. We are assuming one term here, so N is 1, I is as it is, and area will be pi times R square, so pi L square by 4 pi square. So it will be I L square divided by 4 pi. That is option D for us. Moving to the next one. A 250 turn rectangular coil. So N is 250. Length is 2.1. Breadth or width is 1.2 centimeter again. Current I is 85 microampere. Subjected to this magnetic field, work done for rotating the coil by 180 degree against the torque is. So field strength is given 0.85 Tesla. So to find the torque and to find the work done, what we need, for torque we have formula M cross B, and for the energy or work done, that is also known as potential energy, it is minus M dot B. So we need M, we already have the magnetic field. So M is NIA. N is 250, current is 85 into 10 raised to power minus 6, and area will be 2.1 by 100 into 1.25 by 100. That is the value of M. Now, as it is mentioned that work done for rotating the coil by 180 degree against the torque. So assume that initial energy of the initially our we can say our coil is at theta degree angle with respect to the coil. So initially our coil is a theta degree angle with respect to the magnetic field. So I can also draw the diagram that if this is our rectangular coil, then its area vector will be something like this. And suppose this is the direction of magnetic field, this is B, this is M, so initial direction is this, and we have an angle theta between them. So initial energy will be minus MB cos theta, and now we have to rotate it by 180 degrees, so final energy will be minus MB cos of 180 plus theta. Now we don't know the initial angle here, but it is mentioned that we have to rotate it against the torque. Means against the torque means system should be in the stable equilibrium, and system is in stable equilibrium when theta is 0. So we assume here that theta is 0. So our initial potential energy comes out to be minus MB, and final potential energy comes out to be minus MB cos 180. Cos 180 is negative 1, so MB. So it will be plus MB, or we can say that change in potential energy delta P, that will be equal to work done, that will be my MB minus of minus MB, so it will be twice of MB. So 2 Value of m is this one, so 250 into 85 into 10 raised to power minus 10 into 2.1 1.25 into magnetic field, that is 0.85, and upon calculation this will give us 9.5 microjoule. That is option A for us. Now let's move to the next one. A rectangular coil of length 0.12 0.12 meter, width is mentioned, n is mentioned, suspended vertically in a uniform magnetic field strength. The coil carries a current 2 ampere if the plane of the coil is inclined at angle 30 degree with the direction of the field. Torque required to keep it stable. So let us first draw the diagram. We have a, we can say that is a rectangular coil. So okay, I have to draw it. Suppose this is our rectangular coil and its plane, or we can say direction of its magnetic dipole moment, is perpendicular to the plane, so it is like something. Now, and its plane of the coil is something like this. This is the plane of the coil. Now, as per mentioned, that plane of the coil is inclined at 30 degree with the direction of the magnetic field. So if we suppose that this is our magnetic field, if this is the direction of the magnetic field, then this angle, inclination of the plane with magnetic field, this angle is 30 degree. When we calculate the torque, we calculate angle between M and B, direction of the magnetic dipole moment and the direction of the field. So here direction between M and B will be this one, and that will be, as we know this, that this angle is 30, so this angle will also be 30, and that magnetic moment is perpendicular to the plane, so this angle is 90 degree, so this angle will be 60 degree. 60 plus 90 150 plus 30 180, so that's the straight line. So torque will be, value of m is nia into b into sine of 60. Sine of 60 is root 3 by 2. N is 50, current is twice 2, area is 0.12 into 0.1 into magnetic field, that is 0.2 into sine of 60, that is root 3 by 2. Solving all of these, we get 0.028 Newton meter. That is option B for us. Let's move to the next one. A current loop in magnetic field experience a torque whether field is uniform or non-uniform, can be in equilibrium in one orientation, can be in equilibrium in two orientation, can be equilibrium in two orientation, one stable while other is unstable. So let us first examine the first statement, that current loop experience torque in uniform or non-uniform field. So now again torque is given by m cross b. So provided that if field is constant, then it will experience equal torque, because suppose we have a rectangular coil here. This is a rectangular coil and this is the wire which is producing here non-uniform field, because this is a long straight wire, so magnetic field due to it changes as per the distance. So this is producing non-uniform field. So this, as we already solved this type of question, that as a whole this wire experiences a attractive force, and these two sides AB and side CD experience, one of side experience upward force and another experience the downward, so they experience a torque, and this torque is along this axis. This torque is along this axis, so this axis is fixed, axis cannot be changed, means orientation is fixed. And it is mentioned that as per this statement, that torque is in all orientation. So that's wrong, that torque is not along all orientation, it's along a specific axis. So we can say here it is x axis, there is no torque along y or z axis. So one is wrong, option one is wrong. Now coming to the equilibriums. So torque again is mb sine of theta. And for equilibrium, we need torque to be zero. And when torque is zero, then when we have theta is equal to 0 degree and theta is equal to 180 degree. When both of these torque is zero, and at 0 degree, it is known as stable equilibrium, because if we displaced it our we can say that is loop slightly from the angle 0 degree, then it will come back to the 0 degree. And if theta between loop and magnetic moment of the loop and the magnetic field is 180 degree, in that case due to slight displacement it will come to 0 degree. So this will 180 degree is case of unstable equilibrium, and this is case of stable equilibrium. So here we have two equilibrium, one is stable and one is unstable, and that is option D for us, can be in two equilibrium. Okay, two orientation, one stable and while other is unstable. Now let's move to the next one. A circular coil ABCD carrying a current I is placed in the uniform magnetic field. If the magnetic force on the segment AB, if the magnetic force on the segment AB is F, the force on the remaining segment BCDA. Now it is mentioned that this coil is in uniform magnetic field. So here magnetic field is uniform, and force on a current carrying coil is given by M, where M is the magnetic moment, into dB by, suppose if we are taking variation along x-axis, then dB by dx. And as here B is uniform, so force should be zero. So total force on this coil will be zero. Now, as per statement, it is mentioned that force on AB part is F. Suppose it is outward direction and it is F. So now, as a whole, total force on this loop is zero. So total force on the remaining part should be in the opposite direction and equal in magnitude, so that it cancels out perfectly. As we know from the force equation, that force is equal to m into dB by dx. Here variation in magnetic field is needed, and as magnetic field is constant, so variation is zero. So if variation is zero, force is zero. And so total force on this loop is zero, or net force on this loop is zero. And force on AB part is mentioned to be F. So on the remaining part, the force should be equal in magnitude and opposite in direction. So if it is F, then it should be minus F. That is option A for us. Let's move to the next question. A closely wound solenoid with 2000 turns area cross section mentioned, current is mentioned, suspended through its center and perpendicular to its length, allowing it to turn in a horizontal plane in a uniform magnetic field of this making angle 30 degree with the axis of solenoid, the torque on the solenoid will be. So normally till now, uh, we had a loop or a coil in which all the wires were close to each other. But in case of a solenoid, the shape of solenoid is something like this. So there is slight separations between the number of turns, but magnetic moment stays the same, or formula for magnetic moment stays the same, that M is equal to NIA. So here M will be N is 2000, cross section area is 1.5 10 raised to power minus 4, and current is 2 ampere. That is the value of magnetic dipole moment. And it is mentioned that magnetic field is this, and it is making angle 30 degree with the axis of the solenoid. Now axis of solenoid is this is the axis of solenoid, and this is also direction of magnetic moment of the this solenoid. And now so magnetic field is something like this is our magnetic field, and this is our magnetic dipole moment, and they have angle 30 degree between each other. So torque will be M cross B, or M is this, so that will be 2 into 2 4 into 1.5, 1.5 into 4, that is 6, into 10 raised to power minus 1, that is magnetic dipole moment, into B, that is 5 into 10 raised to power minus 2, into sine of 30, that is half. So 3, so 15 into 10 raised to power minus 3, or 1.5 into 10 raised to power minus 2 Newton meter is the amount of torque here. Moving to the next one. A square current carrying loop suspended in a uniform magnetic field acting along in the plane of the loop. If the force on one arm is F, that will be the net force on the remaining arms of 3 arms. So again, this is the same question as we solved previously, that as we have a square loop here and mention that field is uniform, so force on this loop will be M is its magnetic dipole moment into dp by dx, or dp by dy, or dp by dz, depending upon the directions we have. But as mentioned, that field is uniform, so it is not varying in any direction. So if it is not varying, changing means total force should be zero on this loop. And if force on one arm is F, then force on all 3 arms in combined should be in the equal and opposite direction, so should be minus F. So option B will be the right answer here. Now let's move to the next question. So let's slide it. A closed loop PQ wires carrying a current is placed in a uniform magnetic field if the magnetic force on the segment, it is placed in uniform magnetic field. So it is clear that total force uh, on this is loop should be zero. Total force on this complete loop should be zero. If magnetic force on the segment PSSR are mentioned, are in the plane of the paper along the direction as shown in the force. So force on QP we have to find out. Now by looking at the diagram and getting having the idea that total force on the this loop is zero, then we can simply assume that F1 is equal to F3. But that's not the case here. Why? Because length of these sides are different. So if length is different, then amount of the force will also be different, but total force as a whole should be zero. So we assume that force on PQ part is FPQ. So it is FPQ plus force on the SR part on SR section is F2, and it is in the negative Y direction. So it is F2 minus J. Similarly, for the QR, it is F3I in the positive X, and on the PS, it is F1 minus I. So F1 minus I, and total force should be 0. So from this we can write FPQ is equal to F1 minus F3 of I and plus F2 of J, that is the vector value, and we have to find the magnitude. So FPQ magnitude will be F1 minus F3 square plus F2 square. That is option B for us. So with this, we end this video here. Again, if you find this useful, helpful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to donate us something, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.